Imagine directing a photorealistic, never-ending movie in real time, right from your laptop. Today, we're looking at the AI breakthrough that makes this impossible dream a reality. Welcome to our podcast, Artificial Intelligence, Papers and Concepts, curated by Dr. Satya Malik.
Yeah, this is it's a truly phenomenal paper we've got to unpack today.
It really is. And, before we really get into the leads, just a quick heads up for you listening. Both of us guiding you through this deep dive today are, well, actually entirely AI generated.
Which honestly feels highly appropriate given the subject matter.
Right. Oh, absolutely. So our mission today is to break down this fascinating research paper detailing a model called Helios.
A massive joint effort.
Yeah, exactly. It's from researchers at Peking University, ByteDance, Canva, and Chengdu Anu Intelligence. And they basically targeted what is widely considered the holy grail of generative AI.
Right, which is creating infinite high-fidelity video in real time.
Which is, it's wild.
To appreciate the scale of that ambition, you really have to look at the severe bottlenecks in current diffusion architectures. We are accustomed to models that output, 5 to 10 seconds of video?
Yeah, if you're lucky. And even those highly constrained pre-computed clips require massive compute clusters.
Exactly. Tens of minutes to render. It is fundamentally a slow, offline batch process.
And that is exactly where Helios completely upends the current standard. Looking to the sources, the sheer numbers here are just staggering. Helios is a 13 billion parameter model.
That is a massive architecture.
Massive, yet it is running at 19.5 frames per second on a single NVIDIA H100 GPU.
And honestly, the physical constraints of hardware make that metric almost hard to believe at first glance.
Right.
Generally, pushing a 14 billion parameter model to that kind of frame rate hits a memory bandwidth wall. The GPU simply cannot shuttle data back and forth from VRAM to the compute cores fast enough.
Yeah, to put that achievement in perspective for you, Helios is running faster than tiny 1.3 billion parameter models.
Which is insane.
Right, and it is a staggering 52 times faster than WAN 14B, which sits in the exact same weight class. They didn't just throw more silicon at this, they fundamentally tore down and rebuilt the pipeline.
Yeah, the architecture modifications are the core of this paper. They bypassed the standard brute force scaling laws to solve not just the speed bottleneck, but the hardest qualitative problem in continuous generation.
We are definitely going to get into the specific mechanics of how they achieved that speed and how they cured the long video generation headache. But before we get to the underlying math, let's take a quick second. This podcast is sponsored by BigVision.ai, a consulting and product development company that helps companies of all sizes build computer vision and AI solutions. You can reach them at contact@bigvision.ai.
All right, so getting back to the architecture. Raw speed is basically useless if the inference output degrades over time.
Oh, completely.
The primary failure mode of long context video generation is a phenomenon called drifting.
Drifting? It sounds innocuous, but in the context of an AI video, it's more like a slow descent into visual chaos.
Yeah, that's exactly what it is. The paper actually categorizes this chaos into 3 specific mathematical failures. First is position shift.
Okay, position shift.
Right. The latent representation of an object just, loses its spatial grounding. So a character positioned in the center of the frame inexplicably slides toward the edge over several hundred frames.
Right, so it just slides away.
Exactly. Second is color shift, where the global color distribution drifts. The RGB values slowly skew, resulting in oversaturated, unnatural hues.
I have absolutely seen that. You prompt a cinematic shot of a forest, and by second 20, it looks like a neon radioactive wasteland.
Oh, we all have. Usually it's this bizarre, deep-fried purple or green tint.
Yeah, exactly.
And the third failure is restoration shift.
So just what, exactly?
This is the degradation of high-frequency details. The model loses its ability to reconstruct sharp edges and fine textures, so it turns a crisp, photorealistic frame into a blurry, smudged mess as the sequence extends.
So since people have obviously been trying to generate longer clips before Helios, how do the standard architectures try to prevent those shifts?
Well, standard approaches rely on post hoc corrections or constrained training. They use error banks to cache and correct deviations, or a technique called self-forcing.
Self-forcing?
Yeah, but the fatal flaw of self-forcing is that the model is only trained on a short temporal horizon, usually about 5 seconds.
Oh, so it just learns to optimize perfectly for that specific window?
Precisely. When you force inference beyond that 5-second boundary, the model encounters a distribution it has never seen, and catastrophic drifting kicks in.
Wow. It's like training a marathon runner by only letting them sprint 100-meter dashes.
That is a perfect analogy.
Right. Like they look great off the block, but they collapse a mile in because they have absolutely no pacing strategy.
Exactly. The mechanism Helios uses to bypass that is explicit drift simulation.
Explicit drift simulation.
Yeah. Rather than trying to artificially constrain the training data to perfect short clips, the researchers intentionally inject simulated drifting artifacts right into the training pipeline.
Oh, wow. So they're forcing it to fail during training.
Right. They force the transformer to encounter position, color, and restoration shifts. That teaches the network how to organically autocorrect and stabilize those distributions over infinite time horizons.
They're basically inoculating the model.
Yeah.
They expose it to the visual virus so the architecture builds an immune system.
Exactly.
And the visual examples in the source material showing this stability are just wild. They have this one test prompt, a man wearing an antique diving helmet and a jetpack, walking on molten lava with a majestic dragon flying behind him.
Which is a rigorous stress test for temporal consistency, given the complex lighting and contrasting textures.
Across hundreds and hundreds of generated frames, the brass on the helmet stays reflective. The lava maintains its fluid dynamics without turning into glowing static, and the dragon remains anatomically consistent.
It's incredible.
Okay, let's unpack this. If Helios uses a first frame anchor to lock in color and identity, doesn't that make the video rigid or static? Are we just dragging a JPEG across the screen?
You'd think so, but the implementation of the anchor avoids that exact trap.
How so?
It does not freeze spatial coordinates or structural geometry. Instead, it tightly constrains the global appearance distribution.
How does that actually function in the latent space, though?
Well, the model retains the mathematical essence or feature embeddings of the subject, the material properties, the baseline lighting interaction, the specific identity tokens.
Okay.
It uses those embeddings as a persistent reference matrix. So it knows the diving helmet is made of reflective brass, but it allows the spatial positioning, the angle, and the dynamic environment reflections to update frame by frame.
Oh, I see. So it separates the material identity from the physical movement.
Right.
But there is another layer to the motion physics here. The sources highlight a fundamental architectural clash that Helios had to resolve between rotary position embeddings and multi-head attention.
Yeah, the interaction between rope and multi-head attention is notoriously unstable in extended contexts.
Because Ropey applies a rotational matrix to inject absolute and relative positional info into the tokens, right?
Yes, and multi-head attention uses that positional data to calculate relevance between different parts of the sequence. But over extreme sequence lengths, like thousands of frames, the relative distance between the current frame and earlier frames becomes so vast that the rotational embeddings just degrade.
The attention mechanism basically loses its temporal map.
Precisely. The attention scores flatten out or hallucinate, causing the model to lose track of the action sequence.
Which looks terrible, I imagine.
Oh, visually, this manifests as repetitive glitching motion. A character takes a step, the model loses its place in the temporal sequence, and it renders that exact same step again in a stuttering loop.
Yikes. So how does Helios fix it?
Helios recalculates how these positional embeddings are aligned and injected, ensuring the mathematical relationship between tokens remains stable regardless of the sequence length. It completely eliminates the stutter.
That structural fix is elegant, but it brings us back to the most staggering data point. We have a 14 billion parameter behemoth maintaining perfect temporal consistency. How is this rendering at 19.5 frames per second?
That's the real magic trick.
Because standard acceleration in diffusion models relies heavily on caching the key value pairs, standard quantization or causal masking. But Helios isn't relying on those conventional crutches.
No, tearing up the conventional playbook was necessary because standard KV caching for infinite video creates an insurmountable memory bottleneck.
Right.
If an AI attempts to cache the full resolution key and value states of every single token over hundreds of frames, you inevitably trigger an out-of-memory or, ooh, crash. The VRAM simply fills up.
The researchers introduced something called multi-term memory patchification to solve this.
Yes, they do.
When reading the paper, the most intuitive way I could visualize this is how human working memory operates. Think about your daily commute.
Okay, yeah.
You don't retain every single granular detail. Every crack in the pavement, the license plate of every car you pass. Your brain would crash. You selectively downsample the memory to key landmarks. Exiting your driveway, the intersection by the coffee shop, the train station. Is that the underlying logic here?
The logic maps perfectly. Mechanically, it functions as aggressive, localized token downsampling. Helios fragments its memory context into distinct scales, short-term, mid-term, and long-term.
And it routes those tokens through different compression ratios.
It does. The immediate previous frames, the short-term memory, are retained at high resolution because immediate temporal consistency requires precise pixel-level alignment.
Makes sense. You need to know exactly where the foot was a millisecond ago.
Exactly. But the mid-term and long-term memory states are subjected to heavy spatial and temporal compression. The model discards redundant information and only caches the landmarks, or the broader semantic context of what happened a minute ago.
By selectively routing and compressing those tokens, Helios extends its context window to 18 segments without overflowing the GPU. It drops the compute overhead dramatically because the transformer has a fraction of the historical tokens to process.
Yeah, the memory patchification prevents the crash, but the actual real-time generation speed at inference is unlocked by a separate breakthrough: adversarial hierarchical distillation.
Right. This is where the math gets incredibly aggressive. Standard diffusion models work by mapping an ODE trajectory, a mathematical curve, from pure noise to a clean image.
Yes.
And following that curve accurately usually requires something like 50 individual sampling steps, meaning 50 heavy passes through the neural network.
Which is the exact opposite of real-time. Distillation is a known concept, but this adversarial hierarchical approach takes a teacher-forced training method to the extreme.
Teacher-forced.
Yeah, a massive teacher model maps out the perfect 50-step numerical trajectory. The student model, Helios, is then heavily penalized for deviating from that mapped curve, but it is forced to traverse the entire latent space in a fraction of the steps.
It essentially learns to leap across the latent space. They slash the required sampling steps from 50 down to just 3.
3 massive strides instead of 50 small steps, with almost zero loss in visual fidelity.
That's unbelievable.
The computational efficiency is so highly optimized that the researchers can actually fit 4 independent 14B models within 80 gigabytes of GPU memory.
Wow.
By stripping out redundancy in both the noisy context and the historical memory, they achieved real-time, infinite diffusion on a single enterprise chip.
Which naturally created a massive problem for the research team. When you build an engine that breaks the established physical limits of AI video generation, the standard benchmarks become useless.
Right. There was no existing metric to test an infinite real-time generator.
The team had to engineer their own proving ground, which they titled Helios Bench. Since the open source community has no equivalent, they structured a rigorous multi-tier evaluation.
Taking a look at the methodology, they designed 240 distinct prompts divided across 4 duration stress tests.
You have the short tier at 81 frames, moving up to a 240-frame tier, a medium 720-frame tier, and a massive 1440-frame test.
And they evaluated the outputs on aesthetics, motion dynamics, semantic alignment to the prompt, and naturalness.
In the results.
The results were definitive. Helios consistently outperformed all open-source baselines. Even operating as a heavily distilled 3-step model, it matched or surpassed the massive offline base models in visual fidelity.
That is wild.
Furthermore, it completely outclassed the smaller 1.3 billion parameter architectures that were previously the only options for anything resembling real-time speeds.
The prompt variety they used really highlights how robust the underlying world knowledge is.
Yeah.
We discussed the diving helmet on the lava, but the aesthetic range is massive.
Totally.
They successfully generated a vibrant tropical fish gliding gracefully through glowing coral reefs, simulating complex fluid dynamics and light refraction.
Which is notoriously difficult for AI.
Then they tested subtle microexpressions, an extreme close-up of a 60-year-old gray-haired man deep in thought, sitting nearly motionless in a Paris cafe.
Maintaining physical plausibility across those extremes is the true test. The model must handle chaotic, high-frequency motion with the fish, and then perfectly anchor the subtle, low-frequency facial geometry of the man in the cafe, all without triggering restoration shift.
They even threw complex architectural geometry at it. One prompt requires a rotating camera view inside a large New York museum gallery stacked with towering vintage 1950s and 1970s TVs playing different broadcasts.
Oh, yeah. The model has to track the spatial coordinates of the room, the screens, and the varying light sources as the virtual camera infinitely rotates.
Analyzing that specific capability, the maintenance of perfect 3D geometry from a text prompt, brings us to the ultimate application of this research. The implications here go far beyond generating a nice video of a museum.
Right, because Helios unifies text to video, image to video, and video to video processing.
It functions as a true world model. And because
Yeah.
it operates at 19.5 frames per second, it unlocks interactive generation.
Yeah.
This is the paradigm shift for you listening. Interactive generation means you aren't typing a prompt, hitting enter, and waiting for an MP4 to render. Because the generation is real-time, you can dynamically intercept and modify the prompt while the video is generating.
Exactly. You can start with the man in the Paris cafe, and as the model is outputting the video feed, you inject a new prompt. It starts pouring rain, or he stands up and leaves.
That adapts.
The simulated world reacts to your input instantly, seamlessly updating the latent representation without breaking the video feed.
Think about the impact that has on creative software or video games. We are looking at a future with no pre-rendered cutscenes, no static environments.
Right.
You are the real-time director of a photorealistic, continuously generating reality that bends to your exact specifications the millisecond you provide new data.
Which leaves us with a profound technical and philosophical implication to consider. If a model can generate infinite photorealistic video that can be changed midstream with a text prompt, what happens to the concept of a finished movie? Will the entertainment of the future be a static file you watch, or a fluid world that reacts to your mood in real time?
That is a staggering concept to process. The idea that video generation isn't just a medium for entertainment, but maybe the future interface of computation itself. We want to warmly thank you for tuning in to this deep dive. If dissecting the architecture behind these massive leaps in technology is exactly what you're looking for, please make sure to subscribe to the show for more explorations into the absolute cutting edge of AI. Until next time.